Properties of rational functions. For a rational function, the domain is the set of all real numbers except for those where the denominator is 0. So let's look at that with this first function. F of x equals 3x times the quantity x minus 1 all over 2x squared minus 5x minus 3. So first, we need to look at the denominator and factor it. This factors to 2x plus 1 times x minus 3. Next, we'll set each factor equal to 0, and then we'll solve for x. So in the first equation, I'll subtract 1, 2x equals negative 1, divide both sides by 2, x equals negative 1/2. In the second equation, add 3, x equals 3. So these two values, negative 1/2 and 3, are not elements of our domain. So we could write our domain as the set of all real numbers, that's what that fancy looking R means, where x does not equal negative 1/2 and x does not equal 3. Or using set notation, we could write the set of all x's such that x does not equal negative 1/2 and x does not equal 3. We could also use interval notation, but I'm just going to use set notation right now. Okay, let's also be able to look at a graph and identify several of its attributes or properties. So given that we have this graph and those dotted lines are representing asymptotes, let's identify the domain. So the only place on this graph where we do not have x values that have defined y values are where we see the vertical asymptotes at x equals negative 3 and x equals 3. So our domain is the set of all x's such that x does not equal negative 3 and x does not equal 3. For the range, we have two different areas where we see y values on this function, which is the blue graph part. It's the set of all y's such that y is less than negative 3, so below that horizontal asymptote. And then above the horizontal asymptote, we do see a shape where the lowest y value is negative 2. So y is greater than or equal to negative 2. Intercepts. So we're looking at x and y intercepts. So first, for x-intercepts, we have two of them. One is at about negative 2.50 and the other is at 2.50. And again, those are approximate. I don't think they're exactly negative 2.5 and positive 2.5, but given that we don't have an equation, we can only give an approximate answer here. For the y-intercepts, we have 1, which is at 0, negative 2. Horizontal asymptote, we have 1 at y equals negative 3. Vertical asymptotes, we have 2. One's at x equals negative 3, and one is at x equals 3. Oblique asymptotes, that would be like a diagonal or slanted dotted line. We have none. If you have a horizontal asymptote, you're not going to have an oblique asymptote. It's one or the other, although you may have neither. Okay, now let's look at a graph where we are graphing a rational function using transformations. So here we have f of x equals negative 1 over x squared plus 4x plus 4. Okay, so we're going to start by factoring the denominator. The denominator factors to x plus 2 quantity squared. So this function is the same as negative 1 over x plus 2 quantity squared. If we set the denominator factors equal to 0, so x plus 2 equal to 0, and solve for x, we get x equals negative 2, and that is the only value excluded from the domain. So our domain is the set of all x's such that x does not equal negative 2. Before we identify the other properties, let's graph this. So first, let's identify the parent function. Here it would be f of x equals 1 over x squared. And this graph would have a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. So I can plot 3 clear points in different parts. And it's hard for me to hand draw in accurately a graph and not make it look like it's bouncing away from the asymptotes, because it should be approaching the asymptotes. But we have a graph with 2 branches like we see here. And I did plot that using 3 clear points in each branch. Okay, we have 2 transformations. First one we'll look at in the order of operations is shifting this graph left 2 units. So I'm going to move, first I'll move asymptotes. My vertical asymptote moves to x equals -2. My horizontal asymptote doesn't move at all. And then I'm going to take each of those 6 points that I had plotted and move it left 2 units. So I have one branch shifted over here, and my second branch over here. So I just clearly shifted everything left 2 units. And then the negative is a reflection over the x-axis. So my asymptotes will not move, because if I reflect them over the x-axis, they are going to stay where they are. But all of the points that are in the first 2 quadrants are going to shift to quadrants 3 and 4. So if I reflect them over the x-axis, you can see where they're landing, and this is what my end result looks like. So the blue graph is the graph of my function. Now it's easier to identify the range, and we can see that on this blue graph we have values plotted for every y value that is less than 0. So our range is a set of all y's such that y is less than 0. We can see our horizontal asymptote at y equals 0. We can see our vertical asymptote at x equals -2. Again, we do not have an oblique asymptote. Finding vertical asymptotes. So first, we'll simplify the rational function so it's in lowest terms. That would involve factoring and canceling out common factors. Then x equals r, where r is a real 0 of the denominator, would be the equation of vertical asymptotes. Finding horizontal asymptotes. The degree of so we've got different possibilities here for horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will always be y equals 0. So for example, let's look at our function f of x equals 4x squared over x cubed minus 1. Let's start by factoring the denominator. This is a difference of cubes, so it factor to x minus 1 times x squared plus x plus 1. So to find our domain, let's first set our denominator factors equal to 0 and solve for x. In the first equation, we add 1, we get x equals 1. Second equation does not factor, which tells us this is probably going to be a complex number, but just to be safe, realize you can solve this using the quadratic formula or completing the square. We would get -1/2 plus or minus the radical 3 over 2 times I. So we have 2 complex solutions there which do not come into play on the graph in terms of a vertical asymptote. So we have one vertical asymptote, and that is at x equals 1. Finding our horizontal asymptote, well, the degree of our original numerator was 2. The degree of the denominator was 3. So the degree of the numerator is less than the degree of the denominator. That means our horizontal asymptote is y equals 0. Okay, so now let's look at another case for horizontal asymptotes. We could have the case where the degree of the numerator equals the degree of the denominator. When that's the case, the horizontal asymptote is y equals the ratio of the leading coefficients. So let's look at f of x equals 3x plus 5 over x minus 6. Nothing can be factored here. Let's find our vertical asymptote by setting the denominator equal to 0. Add 6 to both sides, we get x equals 6. And that is the equation of the vertical asymptote. Now let's look for our horizontal asymptote. So the degree of the numerator is 1 and the denominator is 1. So y equals, I take the leading coefficient in my numerator, which is 3, over the leading coefficient in my denominator, which is 1. So y equals 3 over 1, or y equals 3, is the equation of my horizontal asymptote. Okay, we have a third possibility with horizontal asymptotes. The degree of the numerator equals the degree of the denominator plus 1. So the numerator's degree is 1 more than the degree of the denominator. Then we would have an oblique asymptote where y equals ax plus b, and that is found by looking at the quotient found when using long division. Okay, so let's look at that in this example. F of x equals x cubed plus 1 over x squared minus 5x minus 14. Let's try to factor everything. The numerator, as a sum of cubes, factors to x plus 1 times the quantity x squared minus x plus 1 over the denominator factors to x minus 7 times x plus 2. Nothing cancels. We have no cancel factors. So to find our vertical asymptotes, take each factor in the denominator, set it equal to 0. In the first equation, we'll add 7 and get x equals 7. In the second equation, we'll subtract 2 and get x equals negative 2. So we have two vertical asymptotes, one at x equals 7 and the other at x equals negative 2. Now let's identify the oblique asymptote. We see that the degree of the numerator is 1 more than the degree of the denominator. 3 is 1 more than 2. So that means we will need to do long division. I'm taking x cubed plus 1. I'm putting 0 placeholders in for the quadratic and the linear term. And then we are dividing that by x squared minus 5x minus 14. What times x squared equals x cubed? I would multiply that by x. So now I'm going to multiply x by all parts of my divisor. So x times x squared, x times negative 5x, x times negative 14. And I get x cubed minus 5x squared minus 14x. I'm going to subtract. So I'm going to change the sign of everything and now add. My x cubed terms cancel out. 0x squared plus 5x squared leaves me with 5x squared. 0x plus 14x gives me 14x. And I will now bring down the 1. What times x squared gives me 5x squared? That would be positive 5. I'll now multiply 5 times all parts of my divisor. So 5 times x squared is 5x squared. 5 times negative 5x is negative 25x. 5 times negative 14 is negative 70. Going to subtract. So I will change all the signs and add. My 5x squares cancel out. 14x plus 25x is 39x. 1 plus 70 is 71. So my remainder is 39x plus 71. Well, for our oblique asymptote, we don't care about the remainder. What we do care about is the quotient, that is x plus 5, found at the top of the dividing box. So the equation of our oblique asymptote is y equals x plus 5. Okay, finally, we have one more possibility where the degree of the numerator is greater than the degree of the denominator by 2 or more. And that means that we would have no horizontal or oblique asymptote. So an example of this would be f of x equals x to the fourth over x squared minus 7x plus 12. Let's start by factoring the denominator into x minus 3 times x minus 4. We can find our vertical asymptotes by setting each factor equal to 0. Solving for x, I'll add 3 in the first equation to get x equals 3. In the second equation, I'll add 4 to both sides and get x equals 4. So this function has two vertical asymptotes, one at x equals 3 and one at x equals 4. And the degree of the numerator is 4, the degree of the denominator is 2. That is 2 more, so the degree of the numerator is 2 more than the degree of the denominator. So there is no horizontal asymptote and no oblique asymptote.